Hello everyone. Now I have finished explaining chapters 7 and 8. I will start solving problems of chapter 7. First I will solve problem 13, page 210. This problem says a particle is subjected to a force Fx that varies with position as in figure P7.13. Find the work done by the force on the particle as it moves from x equals 0 to x equals 5, from x equals 5 to x equals 10, C from x equals 10 meters to x equals 15 meters, and D what is the total work done by the force over the distance from x equals 0 till x equals 15 meters. So first I will start by revising the formula of the work done by a force when the particle moves from a position A to a position B is F equals integral from A to B F dot dr. So the work from A to B for a certain force is equal to integral from A to B F dot dr, which is equal to integral to Fx dx for sure from A to B plus Fy dy plus Fz dz. In our problem, the motion is along x-axis, so dy and dz are zeros. I can get rid of them, and if I'm going to solve, I will write the work of F, in our case, the work of F is equal to the integral of Fx dx. And don't forget the boundaries, no integral in physics without boundaries. Okay, let's start with the first one. For x between 0 and 5, the work of the force F is equal to the integral of Fx dx. We have Fx as a graph as function of x, so I can find f of x in terms of x. I can find the equation of the straight line in terms of x. It's simply a straight line passing through the origin. So I find the slope, then I write Fx equals ax. When I substitute f of x by its value, so I can get integral of ax dx. I integrate simply and I find the answer, and my x varies from 0 till 5. Don't forget the boundaries, okay? There is a second method which says that the integral for a function dx, it's the area under this curve. This is equal to the area under curve. So we can simply look at, don't forget we're integrating from 0 to 5. So this is 5 here. Okay, so it's the area under the curve which is in orange. So I will get this triangle. The area of the triangle is for sure base times height over 2. So without finding the equation of the straight line, I can directly write the work as it's equal to the area of the triangle. So we've got here, it's 5 times 3 over 2, base times height over 2. We will get 15 over 2, which is 7.5 joule. Don't forget that the unit of work is joule. This is for part A. In part B, you have to do the same, but for x between 5 and 10. If you look at this part, you can see that f of x is constant. It's equal to 3 Newton. So I can directly apply the formula. It's easy. Work of f, it's equal for integral f of x dx. I will substitute for f of x. It's 3 dx. X varies from 5 till 10. It's equal to 3 outside the integral. Integral of dx, it's x from 10 to 5. So I will get 3, 10 minus 5. I will get 3 times 5. It is 15 joule. Or simply, it is the area under the curve or the straight line, which is the area of the rectangle that you can see. This rectangle has an area of side by side, which is, and the side horn, it is 5, rounding up it's a 3, so 5 times 3 I will get directly 15 joule. By the second method, remember it's the area of the area under the curve, it's under the line, which is a horizontal line in this case. So let's move now to the third part, which is part C. So in part C, you have to do the same for the last part. So as you can see, we can't find the work from 0 till 15 directly by one step. We have to divide it, because in each case we have a different force acting on the particle at each instant, between each interval of time. So now for x between 10 and 15 meter, you can say that this is a straight line, this is a straight line. You can find f of x as function of time. F of x, for sure, it's equal to ax plus b. You find a and b, which are the slope and the vertical intercept, you find them. Or simply, not to find the equation of the straight line and substitute for it, you say that the work of f, it's equal to the area under the curve. I'm talking about this curve, which is a decreasing line. So this is the area under the curve. So for sure, area under the curve with x-axis. So you can see that the area in this case here, it's the area of a triangle, it's base times height over 2. So my base is 5, height it's a 3. So 3 times 5 over 2, I will get 15 over 2 and 7.5 as in the first part. So 7.5 joule. In part D, it says find the total work. As I have said, that the total work is equal to the sum of individual works done by all forces. So it's equal to 7.5 plus 15 plus 7.5, it's equal to 30 joule. Now this is for problem 13. Let me move to problem 14 in the same page. It says a force F equals 4xi plus 3yj Newton acts on an object as the object moves in the x direction from the origin to x equals 5 meter. Find the work done on the object by the force. As you can see, our force is not constant. It contains x and y, so it's a variable force. Once the force is variable, I have to use the formula or the integral form of the work. I can't use simple equation of work, which is F dot displacement. I must use integral F dr, which is the more general formula for the work. So the work of F, it's equal to integral F dot dr, for sure, from the origin to point x equals 5 meter. He said that the motion is in the x direction, so dr, it's equal to dxi. There's no dy, no dz, it's only moving along x-axis, so there's only dxi. So in this case, f dot dr will give me f, it's let me substitute for f. It's 4xi plus 3yj, and this one it's dxi. So you can see there's no j component for the dr vector. I will only, the dot product will give me 4x dx. I multiply I by I plus j by j plus k by k. There's no j in the dr vector, so I only multiply I by I will get 4x dx. Don't forget the boundaries from 0 to 5. So 4 goes out the integral of x dx, it's x squared over 2, and the integral runs from 0 to 5. I will get 5 squared over 2. I will get 2 by 2. I will get 25 over 25 times 2. So I will get 50 joule. Don't forget the unit of work is joule. This is for problem 14. Now let's move to problem 20. Problem 20 is in the page 211. This problem joins a little bit of previous lessons or Newton's laws with this lesson. It says a small particle of mass m is pulled on the top of a frictionless half cylinder of radius r by a cord that passes over the top of the cylinder as illustrated in figure P7.20. If the particle moves at a constant speed, the particle is moving at a constant speed, show that F equals mg cosine theta. Note, if the particle moves at a constant speed, the component of its acceleration tangent to the cylinder must be 0 all the time. So, for sure, if v is constant, the speed is constant, then AT, which is equal to dv by dt, it's the derivative of the speed, will be equal to 0. There is no tangential, there is only a normal component for the acceleration. So an, it's equal to v squared over r. By directly integrating integral f dr, find the work done in moving the particle at a constant speed from the bottom to the top of the half cylinder. So it started from here, from the bottom, and it has, this is the initial position, this is the final position where it arrived, and I have to work to find the work done by this force in moving the particle from the bottom to the top. So this is our problem. First we have to prove F, to find F. To find the force, I have to think about Newton's laws. Remember that we are moving in a circular motion. The particle, which is colored in orange, is moving on a circle. So in the case of a motion on a circle, remember that we use Newton's second law and never Newton's first law, always Newton's second law. So let's apply Newton's second law. This is part A. Apply Newton's second law. First I have to check the forces acting on equals ma, the forces acting on my particle. What are the forces acting on the particle? I will draw them. We have the weight, which is vertically downward. This is the weight. It's vertically downward. This is mg. We have the normal. Remember the normal بيجي دايما مع الار، يعني بيجي كأنه perpendicular على السيركل. This is n. رسمته لبرا لأنه البارتيكل موجودة على السيركل من برا. لو البارتيكل طاية موجودة على السيركل من جوا برسمه لجوا، موجودة البارتيكل من برا برسمه لبرا. وأنا عم شد بفورس F. So this is my force F. It's tangent to the circle. Okay, as he had said. He said it's tangent. أنا عم شد البارتيكل. So these are the forces acting on my particle. Because the circle or the trajectory, which is a circle, which is a circular trajectory, lines in the vertical plane, I choose two axes, which are, I will draw them. The centripetal axis, دايما الcentripetal axis بيكون اتجاهه لجوا. This is the centripetal axis. وتاني axis هو اللي بيكون التangential axis. Remember, tangential and not the z axis. Z axis بيكون لما تكون الدائرة بالhorizontal plane. هون نحن عندنا الدائرة بوجهنا. So it's in the vertical plane. هيدي tangential. This is the tangential. And this is the centripetal. هلا كل شيء على السنتريبيتال بيساوي A normal وكل شيء على التانجنشال بيساوي A tangential, but in my case A tangential is 0, so it will be equal to 0. Let me write the forces. We've got three forces, which are F plus N plus mg. It's equal to ma. So let's project along the tangential direction because we are searching for F. Projection along the tangential direction. Okay. أكيد أخذت التangential مع الموشن. Remember, so plus F. بالنسبة للangles, let me take another color. Okay, let's keep using blue. So this is theta. For sure, this is pi over 2 minus theta, and this one here is theta. because we have a 90 degrees, so this one is theta. I hope it's clear. I will erase this. Okay, so this one is theta. بالنسبة للprojection I will remove this vector F. الام جي راح تنفصل لجزئين، جزء راح يكون مع التنجنشال، جزء راح يكون مع السنتريبيتال. الشقفة اللي راح تكون مع التنجنشال هي كوساين ثيتا، هي ام جي كوساين ثيتا، so it's minus ام جي كوساين ثيتا. ليه minus؟ لأنه opposite the direction of motion of the particle, so it's minus ام جي كوساين ثيتا. remember إنه الثيتا مع البوينت هي 90، البوينت مع جارتها كمان لازم يكونوا 90 because they make a right angle, so for sure the angle with the tangential is theta. يعني هيدي الانجل اللي ما بين الام جي والتangential axis is theta. so F minus mg everything على التangential بيساوي ma tangential، بس أنا بحالتي ال a tangential is 0 so it is equal to 0. so thus we prove that F equals mg cosine theta. This is the thing he was asking about. In the second part he says find the work when we move the particle from the bottom till the top of the half cylinder. So B, we're searching for the work of F. Remember that if my force is not constant, it's variable, I have to use the integral form. So look at the force F. F is a function of theta. كل ما الانجل تتغير ال F بتتغير. So F is not constant, it's variable. So I have to write it as the work as the integral form. So the work is equal to integral F dot dr. Okay. هلا كل مرة بيكون عندي الموشن هي على circle, it's very common to use dr هي small displacement على circle. So dr it's equal to r d theta. I will draw it here. If I'm moving on a circle, this is dr. It's similar to ds. Okay, أنا مشيت مسافة كتير صغيرة. هيدي الدي ار عندي it's equal to ds. It's equal to r d theta. r is the radius of the circle and d theta is the angle that I have moved. I moved a very small distance. هيدي distance it's يعني نقطة تقريبا إذا بدكم. It's not an arc ولا إنها هي segment ولا يعني فيني حتى أقول عنها straight line. It's a very short distance, so it's okay to say ds or dr. So dr all the time we see such problem we use dr equals r. If we are moving in Cartesian coordinate system we use dr equals dxi plus dyj plus dzk. If we are moving on a circle and everything is written in terms of polar coordinates, I use dr equals r d theta. This is easier. So you can see that F and dr have the same direction. So if I want to draw dr راح تجي هيك. هيدي dr small displacement. طلعوا ال F and dr, they are both tangent to the circle, they have the same direction, so it's F dot dr times cosine 0. Cosine 0 is 1, so equals integral. I'll just fix my integral. F dot dr. So I replace now everything in terms of the given mg cosine theta, and I will replace dr with r d theta. If you look, we have m constant, g constant, r is constant, so the only variable is theta. بس الvariable الوحيد هو theta, and this theta varies from 0 till 90. Okay, from 0 till 90 or till pi over 2. Why? Because أنا مشيت من ال bottom till the top. So in this case from 0 till pi over 2. Don't forget the boundaries. Okay, it's equal to, as I have said, mgr are constants from 0 till pi over 2 cosine theta d theta. It's equal to mg integral of cosine sine theta from 0 till pi over 2, so it's mgr sine pi over 2 minus sine 0. Sine 0 is 0 and sine pi over 2 it's 1, so it's mgr. And this is the answer. بس قبل ما انتقل للسؤال اللي وراه بدي اقول شغله صغيره. الدي ار هي small displacement on the trajectory، يعني لما تمشي البارتيكل شوي صغيره على trajectory. انا عم بعمل انتجرال f dot dr، يعني عم بحسب الورك لما تمشي شوي شوي لحتى تخلص كل المرحله اللي هي لازم تمشيها. ليه بعمل هيك؟ لانه الفورس تاعتي هي variable، so it's the only way to calculate the work. كرمال هيك الدي ار بتكون tangent للتراجكتوري، لانه مثل ما شايفين انتو دي ار small displacement، اكيد small displacement will always be tangent to the trajectory. مثل ما حكينا بالدرس القديم اذا بعدكم ذاكرين لما حكينا عن displacement قلنا delta r it's the position او the displacement vector that joins initial with final position. لما تكون الدلتا r كتير صغيرة it becomes dr and this dr is always tangent to the trajectory. Okay, it's a small, very small displacement. Let me now move to the next problem. I will do problem 32, page 212. This problem says a 2 kilogram block is attached to a spring of force constant 500 Newton per meter. So the force constant is the stiffness constant. It's K. I will write the given. We have M equals 2 kilogram. We have K, spring, it's equal to 500 Newton per meter. As in figure 7.10. The block is pulled 5 cm to the right of equilibrium and released from rest. Find the speed of the block as it passes through equilibrium if the horizontal surface is frictionless and the coefficient of friction between block and surface is 0.35. No unit for sure for the coefficient of friction. Okay, there's no figure, I know, because I have to draw one. It's a simple problem with a block attached to a spring, the spring attached to the wall from the other side. This is my case. Block attached to a spring. The block was pulled 5 cm to the right of equilibrium and released from rest. So we can say that x0 was equal to 5 cm. This is x0. It's 5 cm. It's 0.05 meter. What should we find? We have to find the speed of the block as it moves through the equilibrium position. The easiest way to solve such type of problems each time he asks about the speed is to use the conservation of mechanical energy if there is no friction, and use delta E mechanical if there is a friction. Okay, this is the easiest method. Anyway, there are too many methods. You can solve in the way you like, or the way you feel it's easier for you, or it's easier for you to understand. I don't care, you only care for the right answer and for sure for the correct way, but the right answer. Let me start by part A. In part A, he said that the surface is frictionless, so we have no friction. If we have no friction, that means we have no non-conservative forces. No non-conservative forces. What are the forces acting on the particle or on the block? They are the weight, the normal, the tension. All these forces are conservative forces, so I can say that the mechanical energy is conserved. EM is conserved. I can say that E mechanical initial it's equal to E mechanical final. I'm saying initial and final, I mean initially when he was here, we had stretched with x0, this is the initial position, and this is the initial position, and final, it's not final, it's the step where I'm searching for it, when it passes in the equilibrium position. شو يعني equilibrium position؟ هو البوزيشن اللي بتكون فيه السبرينج مرتاح، يعني لا stretched ولا elongated. There's no elastic potential energy. So I just apply the formula. It's EK plus EP E plus EPG, for sure initial, it's equal to EK. I will write them directly like this, بعدين بصير بختصر plus EPE final plus EPG final. نحن اتفقنا انه الريفرنس ما بيأثر، so رح ناخد الريفرنس ليفل تعولنا مارق بالبلوك. This is the reference level. So رح يطلع مع ال EPG initial EPG final they are zeros, they cancel each other, they are equal. Any way you can think of it in many possible ways and they are all the same. Initially كان هو بده يفلته, it was released, ما دفشه فلته. Okay, it was released from rest. You can see that he said released from rest. So E-kinetic initial it's 0. This one is 0. لما كنا بالاequilibrium position, which is finally, I'm writing it as finally it is 0, the elastic energy. Why? Because the spring is not elongated, not compressed. So for sure EPE at the second case is 0. So what remains is half EPE initial, it's equal to half, it's equal to EPE EK final. So half K x0 squared equals half V z squared. We're searching for V, half with half, it is cancelled. I will get V, it's equal to radical K over M x0. Substitute, you will get 0.79 meter per second. And this is the answer. This is for in the case where there is no friction. In the second case, he says the coefficient of friction between the block and the surface is 0.35. So he's giving us friction. There is friction. Mu is equal 0.35. كل مرة بيكون في friction. Before talking about this part, I'd like to solve the first part in a different way. Let me erase and solve the first part in a different way. A second method, you can use any method I said you like. Second method, you can use the work energy theorem. They are all the same, energy theorem, but I prefer the first one, theorem. Yeah, you'll see me solving using the first one. I feel it's easier and it causes less mistakes for students, so I usually use it. The work energy theorem says the sum of works of external forces it's equal to delta EK. Okay, so how many forces are acting on my block? There are 3 forces, which are the tension, I have the weight, I have the normal. Okay, it's equal to delta EK, which means EK final minus EK initial. Remember that EK initial was 0. كمان الwork للweight والwork للN are also zeros. ليه? I will go back to the figure. Sorry. It's here. As you can see, the weight perpendicular مع displacement. وكمان الN perpendicular مع displacement. Displacement كيف is horizontal بينما ال N وال W they are vertical. So when the vectors are perpendicular with the displacement, their work will be zeros. So these works are zeros. Remember that the work of the tension it's equal to half K x initial squared minus half K x final squared. I've given it to you. It's equal to EK final. I'm searching for EK final, which is for sure half mv squared. Remember that x final was 0 لأنه it was unstretched and there is no elongation, no compression. So I've called this x0. It's half k x0 squared equals half mv squared. So we get the same answer as above. V equals 0.79 meter per second. You can see it's the same. Let me now move to part B. As I have already said that in part B he is asking me to do the same if there is friction, and this friction has a coefficient of friction mu equals 0.35. So I can use this method, which is for the non-conservation of mechanical energy. I prefer this method. It's delta E mechanical, it's equal to the work of non-conservative forces. How many non-conservative forces do we have؟ نحن اتفقنا انه في عندي كان الويت, tension, normal and friction. كلهم conservative ما عدا الفريكشن هي non-conservative. So we can say it is the work of friction. Delta E, it's E mechanical final minus E mechanical initial equals the work of friction. هلا E mechanical final اتفقنا نحن بالفاينالي ما عندي بس الا E kinetic, ما في عندي شيء تاني. So I will directly substitute. ما عندي بيكون finally ما عندي elastic, ما عندي EPG, I only have kinetic. So it's half mv square minus initially it was stretched released from rest وما في EPG, يعني ما في V وما في كان EPG, ما كان عندي EK وما كان عندي EPG, عندي بس كان EP. it's half kx squared. I'm writing them directly because I have explained them up. half kx0 squared. The work of friction, هلا in our case we are assuming that friction is a constant force, so its work, it's as I have explained, it's minus Fr times the distance which is traveled. What distance is traveled? It is the distance which is x0, which is d. لأنه أنا كان ممدود مسافة x0 ورجع للإكوليبريوم position, so for sure he traveled a distance which is x0. He did not give me Fr, but for sure there is a relation between Fr and mu. Remember, this is the tension, هيدي normal, هيدي الويت, وهيدي الFR, because it's moving this way. طيب بالنسبة لإلي أكيد كل شيء على vertical will be equal to 0, so n minus w it's equal to 0, so for sure n it's equal to mg. Remember that Fr it's equal to mu n, so Fr it's equal to mu mg. هيك بربط ال Fr بال mg لأنه أعطاني هو الميو. So let me write implies half mv squared minus half kx0 squared equals minus mu mg x0. I guess I have everything. I have m, I have k, I have x0, I have a mu. Substitute. Don't forget to substitute for G 9.8. In exams we usually use 10 and not 9.8, but here I use 9.8 as in the book. So you will get your answer. V is equal to 0.531 meter per second. Look that the speed has decreased because there's friction. إذا أنا بقارنها مع فوق طلعت معي 0.79 هون تحت 0.53. In the second case it's less due to the presence of a friction. And don't forget this is the kinetic friction. This is a kinetic friction so that you can remember it's in UK. It's in UK everywhere. Okay. For sure you can use other methods to solve the same problem. You can use the method of work energy theorem, some work extra, but you have to include the work of a friction. You can use the upper methods to find it's كمان the same. كمان بالطريقة الأولى فيكم تعتمدوا كمان بهي الطريقة. في طريقة ثالثة إنه أنا فيني أعتمد هون aside. Let me write it. You can use إنه delta EP delta EK equals minus delta EPE. فيكم تستعملوا هيدي لأنه كل شيء كان kinetic تحول، كل شيء كان elastic تحول لkinetic، so اللي خسرناه هون elastic صاروا kinetic. So this formula comes from here, so I will write it in a proper way. It is delta EK equal minus delta EP. But I prefer the first method. Anyway, I will write it. It's half mv squared minus 0 equals minus 0 minus half kx squared. So بيطلع معي بالآخر half mv squared equals half kx squared. Remember delta ek هي ek final minus ek initial, والدلتا EPE هي EPE final minus EPE initial. Final minus initial for sure هيدي 0. Okay, this is the answer. يعني أي طريقة حليته أنتو, it will give me the same answer, but you can use anyone you like, anyone you feel it's close to you. Let me now move to problem 35, page 212. This problem says a slid of mass m is given a kick on a frozen pond. The kick imparts to it an initial speed of 2 meters per second. So the initial speed, the initial, it's equal to 2 meters per second. The coefficient of kinetic friction between a sled and ice is 0.1, so mu k is equal to 0.1. Use energy considerations to find the distance the sled moves before it stops. So we have to find the distance that this sled moves on ice. This is a sled or a box, anything. This is the ground. Okay, it will move and it will stop when its final speed is equal to 0. So it starts with an initial speed and ends up with a final speed 0. We have to find the distance traveled. Because we have a friction, we will use delta A mechanical equals work of non-conservative forces. Let's see what are the forces acting on the sled. We have the weight, which is vertically downward. We have the normal, and we have the friction, which is opposite, the kinetic friction, which is opposite to motion. So let's apply the formula. Delta E mechanical equals work of non-conservative forces. The only non-conservative force is the friction, so it's equal to the work of the friction. E mechanical final minus E mechanical initial, it's equal to work of friction. Initially or finally ما في عندي kinetic, so EK finally is 0. Finally EPG راح اعتبره 0. This is my reference level, so EPG it's equal to 0. ما في عندي elastic energy, so finally it's 0. Minus E mechanical initial, كان عنده speed يعني في EK. ما كان في EPG لأنه أخذت reference على الجراوند. وكمان ما في عندي elastic, so it's half mv initial squared. It's equal to work of friction. If friction is a constant force, it's work, it's equal to minus fr times distance traveled, which is the distance I'm searching for. هلا الفريكشن ما معي اياه، هو معطيني ميو كي. نحن بنعرف انه the sum of forces along the vertical it's equal to 0. يعني n we have n minus w equals to 0 because there is no motion along y-axis. راح يطلع أنا عندي implies n it's equal to w it's equal to mg. So بس نعرف ال n بصير فينا نعرف ال kinetic friction. I've called it fk. Let me call it fk everywhere. So it's fk. It's fk dot fk equals to mu k mg. So now I have fk. I can substitute. I will get then minus half mv initial squared equals minus mu k mg d. So minus with minus, they are cancelled. I will get d equals mv initial squared over 2 mu k g. Okay, we substitute, we get 2.04 meter, and this is the distance. كل مرة هلا هو قال لي use the energy consideration. هيك أسئلة هل بتنحل باستعمال نيوتنز second law كل مرة بنشوف هيك نمط من الأسئلة you know that there are two ways of solving problems مثل ما أنا قلت قبل. We can solve them either using Newton أو using energy considerations. بالعادة لما يسألني لما يكون بالسؤال معطيني speed أو بيقول لي speed بفضل أنا استعمل الانرجي لأنه الانرجي فيها half mv square. بينما إذا سألني عن الاكسلريشن أو سألني عن الفورسز بشكل مباشر أنا بفضل استعمل طريقة تانية طريقة نيوتن مثل ما كنا نشتغل بتشابترز 6 and 5 and 6. So let me allow you to see a second method. So it's a second method, but I prefer the first one, but the second one is not wrong also. I will repeat again. بس يطلب مني بالسؤال speed أو يعطيني سبيد الافضل انه انا استعمل الانرجي كونسيدريشنز. ممكن نفكر بالناحيه انه انا استعمل الانرجي كونزرفيشن او نون كونزرفيشن اوف انرجي. اذا معطيني بالسؤال او طالب مني الاكسلريشن بفكر بنيوتنز لوز نيوتن's second law. So let's apply Newton's second law. sum للاف على هيدي السليد external equals ma. We have three forces which are friction plus weight plus n is equal to ma. Let's project along x and along y. So نحن هيك كان معنا الFK backward مع normal مع weight وأنا الموشن هي to the right. So this is x axis and this is y axis. ما تنسوا x axis مع الموشن. minus fk equals ma عندي n minus w is equal to 0. هيك بكون أنا جبت ال a. So implies a is equal to minus fk over m. طلعت معي negative ال a لأنه عم يعمل deceleration وكمان بيطلع معي it's equal to minus mu k n over m. It's equal to minus mu k n هي mg over m. It's equal to minus mu k g. اوكي لقينا ال A. شو نوع الموشن؟ uniformly decelerated rectilinear motion لأنه ال A is negative. So I can use the formulas that I know for UA RM and U for UA for UD RM. Let me write them. The motion is uniformly decelerated rectilinear motion. So I can use any formula of the three formulas that we know for uniformly varied rectilinear motion. Because I'm searching for the distance وما معي time وأنا ما بيهمني time, I will use the formula which is time independent. V squared minus V initial squared V final squared minus V initial squared equals 2a x minus x final minus x initial, which is d. So this will get V final squared, which is 0. I will substitute directly. x0 squared minus V initial squared. V initial, I guess it was given, I will leave it like this, equals a had a value mu k g, and x final minus x initial is the distance I'm searching for. So it's d. I will substitute it with d. معي كل شيء. So I will get implies d equals v initial squared over 2 mu k g. If you calculate the number, you will get the same number as up. So it will give me the same answer as above. I will move down to problem 39, page 212. This problem says a skier of mass 70 kg is pulled up a slope by a motor-driven cable. How much work is required to pull him a distance of 60 meters up a 30-degree slope assumed frictionless at a constant speed of 30 meters per second? B. A motor of what power is required to perform this task? So I have a skier. The skier is going upward. I'm drawing it as a block, but it's a skier. So the mass of the skier, it's 70 kilogram. It's going up an inclined plane. The inclined plane has an angle of 30 degrees, and he's going to move upward a distance of 60 meters. This is 60 meter, and we have no friction, so there is no friction. At the speed of the skier, it's v equals 2 meters per second. It has a constant speed, so its motion is URM. It's moving in uniform rectilinear motion. What do we have to find in the first part? We have to find the work required to pull this skier this distance, and the work done by the force pulling the motor or anything that's pulling this skier upward. So to find the work of this force, first there are several methods. We don't know the force, we can find the force. And then try to apply integral f dot dr or f times displacement. Okay, this is one way of finding the work of the force, but there's another method which is a little bit easier, because we are studying our lesson is about energy, so we will use energy. I will try to use the formula that we know, or the formula that we love to apply, which is the formula of the mechanical energy. أول سؤال حدا بيسأل حاله هل الميكانيكال energy is conserved or what are the forces acting on this skier at first. في عندي الأف اللي عم تشده لفوق، في عندي النورمال، في عندي الويت، وفريكشن قلنا ما فيه. طيب الويت conservative، الأن conservative. هل الأف conservative force؟ No، لأنه أنا قلت الميكانيكال فورس pushing pulling هيدول منهم conservative. So بهيدي الحالة the mechanical energy is not conserved. I use the formula delta E mechanical equals the work of non-conservative forces, which is the work of F. I can find the work this way. This is an easier method. So ليه non-conservative work البولينج البوشينج كل شيء مثل هيدا بيكون عم يعطي energy للسيستم، فهيدا بيكون it's giving energy to my system. It's not conserving the mechanical energy, it's somehow giving energy to my system. So E mechanical, if you want, E mechanical final minus E mechanical initial, it's equal to work of F. So EK final plus EPG final. وعندي هون elastic energy، عندي بس kinetic و gravitational potential minus EK initial plus EPG initial, it's equal to work of F. Remember I'm searching for the work of F. في عندي شغلة مهمة إنه عندي EK final it's equal to EK initial because it's moving with a constant speed. So these two terms will cancel each other. This term will cancel this term. بيبقى عندي EPG final minus EPG initial, which is equal to mgh final minus mgh initial equals work of F. It's equal to mgh final minus h initial. I've taken mg common equals work of F. If I look here, okay, I'm taking my reference here, this is my reference level, so this is h initial and it's going upward, so this is h final. So h initial or h final minus h initial, you can see it's in reality the difference in heights. This is, I will call it h, so it's mgh equals work of F, implies there's a relation between h and alpha, which is the angle of the incline. هون الزاوية 30، هون الزاوية كمان 30. They are corresponding. So this is 30. I will call this distance D, the distance traveled by the skier from initial to final position. So we have sine 30 aside. Sine 30 equals h over d, implies h equals d sine 30. اوكي سو بالنسبة لنقطتين بعد عن بعض مسافة d على inclined plane, الهايت difference الهايت between these 2 points on an inclined plane h equals d sine 30, where d is the distance between them, h هو الارتفاع بين هالنقطتين, وsine 30 is for sure the angle of the inclined plane. So I will get mg d sine 30 equals work of f. I guess we have everything. I've already calculated it. You get 20580 joule. Okay, this is for the first part. And the second part, what did he say? He say a motor of what power is required to perform this task? We have to find the power of this motor. To find the power, back to our problem. Okay, we were here. To find the power, we have to define the work by t, by time. So let's find the time. So B, the required time for the skier to move from initial to final position, for skier to move from initial to final position is T equals D over V. اوكي هيدي الفورمولا ما فيني استعملها الا بحالة لما يكون الاوبجكت ماشي ب constant speed. اذا مش ماشي الاوبجكت ب constant speed I have to use the formulas of uniformly varied rectilinear motion, the three formulas that we always use. بس تكون الموشن URM فيني استعمل هالقاعدة اللي هي distance equals V times T. This relation is true only when the object is moving in constant speed. غير هيك منا صح. اوكي هون هو ماشي with constant speed, so T equals D over V. D was already given, it was 60, and V was equal to 2, so it's 30 seconds. صار معي التايم لحتى انتقل from initial to final. Now I can find the power. Power is equal to work of this force. I'm searching for the power of the force over time, so I will get 20580 over 30. I will get 686 watt. So this is the unit of power. Done with this problem. Now let's move to problem 58, page 214. This problem says a particle is attached between two identical springs on a horizontal frictionless table. Both springs have a spring constant K and are initially unstressed. If the particle is pulled a distance x along a direction perpendicular to the initial configuration of the springs, as in figure P7.58, show that the force exerted by the springs on the particle is F equals minus 2kx 1 minus L over radical x squared plus L squared I. So we have to find the force F exerted by the first spring and the second spring on the particle. F1 is the force exerted by the first spring, and F2 is the force exerted by the second spring, and we have to prove this formula. رح ارجع اعيد شو كان عندنا نحن بالبروبلم. لما كانت البارتيكل بالايكوليبريوم بوزيشن، يعني هون كان السبرينج هو هيك، كان السبرينج هيك، اوكي، والسبرينج الثاني كان هيك. سو كل واحد من السبرينجز كان عنده طول L. The springs were initially unstressed. they were not elongated not compressed كانوا مرتاحين. اوكي لما زحت البارتيكل انا شوي زحتها شوي مسافة x so I will remove these so المسافة من هون لهون it's x. اكيد السبرينج يعمل elongation. لما يعمل السبرينج elongation بيعمل force لانه ال F equals k times elongation or compression. So let's try first to call this angle here alpha to make things more obvious. طيب بالنسبة لنا طول السبرينج الجديد أنا معي هون right angle so this x this is L هون راح تكون طول هون x squared plus L squared. Similarly down it's radical x squared plus L squared. This is the new length of the spring. هو صار طوله من بعد ما زاحت البارتيكل مسافة x صار طوله الجديد هالقد. Okay, so we can find sine alpha and cosine alpha in terms of the given. Sine alpha opposite على hypotenuse, so it's L over radical x squared plus L squared, and cosine alpha it's equal to adjacent over hypotenuse, it's x over radical x squared plus L squared. Okay, I will keep these because I will use them when I solve. بالنسبة لل F1 ال F1 لما أنا أعمل projection ال x axis هو directed to the right. So بالنسبة إلي ال F1 I write F1 اللي هو الماgnitude بيرجع عندي or I will write it in the same way you know. So it's minus F1 cosine alpha I plus F1 sine alpha j. إذا أنا بحاول أفصل ال F1 I will try to decompose it here. This is F1 هلا برجع بمحيها وهيدي الألفا هون. لما أفصل ال F1 رح يطلع عندي شقفة upward وشقفة to the left. So هيدي اللي هون هي minus F1 cosine alpha وهيدي اللي هون هي F1 sine alpha. Don't forget the signs, okay? Don't forget the signs. The same as projection. بس أنا بحط I و J. هنا بالprojection بكتب ال I لحال وال J لحال. Here I'm writing them as vectors. Let me erase. This is F1. F2 نفس الفكرة راح أعمل أنا راح أعمل plus ال F2 عندي ال X negative وعندي ال Y negative so it is minus I will write minus directly so it's minus F2 cosine alpha I minus F2 sine alpha J. اوكي هلا صار معي ال F1 وال F2 in terms of I and J. بعد بدي أعوض محل الألفا ساين ألفا كوساين ألفا and F1 F2. ال F1 كماجنتيود ما تنسوا أنا بحط F1 أنا already حاطة الساين برا يعني ال F1 this is the magnitude so I only care for the magnitude. ال F1 it's equal to K delta L. Delta L is the elongation. K هي ال stiffness constant of the spring. دلتا ال هي قديه طول السبرينج هي مش الاكس هي قديه طول السبرينج قديه صار طوله الجديد هو راديكال x squared plus L squared قديه كان طوله قبل L so this is delta L elongation of the spring. F2 كمان هي نفس ال K لأنه هو عاطيني إنه both springs have the same K it's K delta L نفس الفكرة it will give me K radical x squared plus L squared minus L. So you can see that F1 is equal to F2. So if F1 is equal to F2 up فيني طير أنا هيدي مع هيدي because F1 is equal to F2. So what remains then F رح تطلع معي minus F I will call it 2 F1 cosine alpha I because F1 is equal to F2 directly. I will substitute it's minus 2 F1 هي K radical x squared plus L squared minus L cosine alpha جبتها من شوي هي x over radical x squared plus L squared I. I'm trying to search the formula اللي هو معطيني إياها عم حاول أوصل لها. I will divide by minus 2kx راح أجيب الx لهون رح أقسم على radical بيطلع عندي 1 minus L over radical x squared plus L squared I. It's the same form given in the problem, so نحن عملنا proof. In part B بيقلنا determine the amount of work done by this force in moving the particle from x equals a to x equals 0. لما مشيت البارتيكل من x equals a to x equals 0 قد ايه the work done by this force. If you look at this force is not a constant force, it's a function of x. يعني كل ما تتغير ال x بتغير ال force. So to find the force, to find the work, we have to use the integral form. The work is equal to integral from a to o f dot dr. Because we are moving along x-axis, so it's fx dx from a, as I said, to o. لأن نحن ماشيين على x-axis, so dr is dxi, and f, you can see it here, this is f, so we only substitute for fx مثل ما هي, this is fx, I just copy it, it's without the I, لأنه أنا ال I طارت مع ال dr, هيطلع معي minus 2k x 1 minus L over radical x squared plus L squared dx. Remember, from a till o, which is 0. Okay, a, it's the distance a, it's equal to the integral I will develop, it's minus 2kx plus 2kxl over radical x squared plus L squared, okay, dx. Don't forget the boundaries from a to o. أول وحدة minus 2 الانتجرال للx هي x squared over 2 from a to 0. تاني وحدة I will use the change of variable. I will use plus, I will write it like this. هلا بعمل change of variable تحت 2kxl over radical x squared plus L squared dx. So الأولى راح أعوض مرة 0, it's equal to, مرة راح أعوض minus ما تصير plus 2k a squared over 2 plus هيدي كيف بعمل؟ باخد change of variable. I will write here aside let u equals x squared plus L squared, then du is equal to 2x dx. مثل ما شايفين راح أحول كل شي ل u. I hope you know how to do change of variable. This is 2x dx, هياها فوق. So راح يطلع معي الانتجرال عندي بيبقى عندي k l du over radical u, it's equal to 2k a squared, okay, 2 مع 2 is cancelled, so it's 2k a squared plus kl integral u to the power minus half du, it's equal to ka squared plus kl, نزيد واحد فوق بصير عندي half over half. Don't forget ترجعوا اليو مثل ما كانت قبل, it's equal to ka squared plus kl, اليو كانت معي x squared, so radical to the power half, it's x squared plus L squared divided by half, so بيطلع عندي هون 2, يعني اسم 2 بيطلع هون عندي 2. وما تنسوا الباوندريز, ما تنسوا الباوندريز which is from a to 0. اوكي, يعني انا رجعت اليو مثل ما كانت x ورجعت عوضت نفس الباوندريز. you can change boundaries, بس انا بفضل هاي الطريقه, it's easier. so k a squared plus 2kl, مرة بعوض 0 بيطلع عندي radical L squared minus 2kl radical a squared plus L squared, مرة بعوض a, so رح يطلع معي k a squared plus 2kl squared في L من هون و L من هون minus 2k L radical A squared plus L squared, and this is the last form.